Okay, so let's begin our second session for today's QFT session, this afternoon session for QFT. And we're very pleased to have Wenjie Ma from Shanghai Semis talking to us about amplitude from crossing-symmetric celestial OPEs. Please take it away.
Okay. Oh, okay. Okay. So thank you. Okay. So basically now on a New Year ADSFP, it's a D plus one dimensional boundary theory, 2D dimensional boundary theory. So basically now it's a D plus two dimensional boundary theory due to a D dimensional boundary theory. And there are some evidences for this holography. The first one is from the point of view of symmetries. We know in finite space-time, the total asymmetry is the full asymmetry is the Pontryagin symmetry, which contains a subgroup of the Lorentz group. And by using group argument, we know the Lorentz symmetry is isomorphic to Euclidean conformal symmetry in deep dimensional space. So this is from the symmetry point of view. And also, if we focus on 4D, I mean the boundary theory is D equal to 4, then the boundary theory is D equal to 2. We know in 2D safety there is a nudge symmetry, which was generated by the Virasoro algebra. And Strominger and his collaborator actually found, and for the Virasoro algebra, you may ask, how do we generate Virasoro algebra on the boundary, because it's larger than this SOD plus 1 common 1. And people already show that if we discuss the asymptotic symmetries in 4D spacetime or asymptotic spacetime, we will find there is a large gauge symmetry. And this large gauge symmetry will generate the Virasoro algebra in the boundary. And so this is from the symmetry point of view of symmetry. That's why we believe there is a holography in flat spacetime. Another view is from the software theorem. People have proved that the software theorem in flat spacetime, I mean the Weinberger software theorem in flat spacetime, can be translated into the one identity in the boundary, which can generate the conformal symmetry. And besides the symmetry, we will also see what's the dictionary relates the boundary theory to the boundary theory. So the most important things are the observables in both theories. On the bound side, we know the most important observables are scattering amplitudes, right? In QFT, we know in QFT. And on the boundary side, I mean, from the knowledge of safety, we know the most natural observables are the conformal correlators. So basically, the symmetric holography gives us a relation between the scattering amplitude and the conformal correlators on the boundary. We call them as symmetric amplitudes. I will show you the relations after. And in my work, we focus on D equal to 2, which means the boundary side is a 4D QFT, which is a New York QFT. And the boundary side is a 2D conformal field theory. And we use the delta to label the conformal dimensions and the J to label the conformal spins. Okay, so then in this slide, I will show you the dictionary, I mean the relation between the two observables. On the boundary side, as I said before, we have the state amplitude. And on the boundary side, we have the conformal correlators, which called celestial amplitude. They are related by, for massive state particles, they are related by these mailing transformations. So here the T is the on-shell moment, on-shell state amplitude, and the Qi are massless on-shell momenta. And we can embed, because the Qi are massless momenta, so basically it satisfies Qi square equal to 0, right? So basically it lives on the line cone. And we can choose the spatial coordinates on the line cone to embed the Qi. So basically we choose the omega I, Zi, which is a spatial choice to parameterize the vectors on the line cone. And the omega I basically plays the role like the energy. And we just perform the mailing transform on the energy of the state amplitude. We can need the so-called celestial amplitude. And this celestial amplitude can be thought as conformal correlators in celestial safety. And so I will introduce some labels on both sides. On the boundary side, because it's a conformal field theory, so it's natural to label it by the conformal dimension and also conformal spins. So we use the delta to label the conformal dimension. Unlike the New York ADS safety, I mean the unitarity demands that the conformal dimension should be real, because unitarity in New York safety demands that the conformal dimension should set greater than some utility bound, which means the delta must be real. However, in celestial safety, the delta is not necessarily to be a real number. It can be an incomplex number. So from this point of view, the C safety is not a unitary theory in the like the New York safety. And here the delta is on the principal series. Basically it's D plus T over 2 plus IR. When D equal to 2, so basically it's 1 plus IR. And this is required by the invertibility and the completeness. So let me explain a bit more about the invertibility and the completeness. So in New York QFT, we know the scatter amplitude in momentum space can be obtained by expanding the S measures with respect to the plane with basis, right? This is what people did in New York QFT. So basically we have for example, for free scalar, we have the scalar in plane space, and because it satisfies the equation of motion, we expand it into the plane with basis, and the corresponding expansion coefficients are just the creation and annihilation operators, right? And then using this creation and annihilation operators, we define the S measures in the momentum space. This is how we did the scalar amplitude in the momentum space. Then we can think about more. The plane with basis actually is the basis of the solution space of equation of motion. That's why we can expand any field operator in terms of this plane with basis, right? It's just a Fourier expansion. But because then we can think about, could we choose another set of bases? Because just a set of bases there's nothing to restrict ourselves just focus on plane with bases. We can for sure choose another set of bases. And for plane with bases, we know it manifests the translation symmetry, which means the translation symmetry is translated into the momentum conservation. So you can see the translation symmetry explicitly, right? However, we know the full symmetry is planetary symmetry, which also contains the Lorentz symmetry. Then it's natural to ask, could we find a set of bases which manifests the Lorentz symmetry? The answer is yes. And this basis is the so-called conformal basis, because the Lorentz group is isomorphic to the Euclidean conformal group. That's why we call this basis as conformal primary basis. This, in terms of this basis actually manifests the Lorentz symmetry. So just follow the same thing as we did in the plane wave basis. We can expand the field operator in terms of this plane wave basis, which also satisfies the equation of motion and forms the basis of the solution space. So we can expand the operator in terms of this conformal basis and define the corresponding Croatian and annihilation operators, but with respect to this basis. And expand the S matrix in terms of these operators. We can get the circular symmetry amplitude. And at this point of view, you may think it's trivial because it's just a change of basis, right? We just using conformal basis in some of the plane wave basis. Then where is the holography? Because it seems like just a change of basis. The non-trivial part of this holography is that, yeah, for sure, for any S matrix, you can do the change of basis and get the symmetry amplitude. But the non-trivial part is we indeed identify this symmetry amplitude as some physical correlators in your CFT. This is a non-trivial part of the dictionary. Although it's just a proposal, nobody have proved that. It's just a proposal. But the non-trivial part is not just a change of basis. We indeed identify this amplitude as some physical CFT conformal correlators. This step, okay. Mm-hmm. Yes, yes.
And also the homomorphic function in the symmetric sphere. Like this is a basis for you.
Also include the boost. Yeah, so this basically manifests the whole Lorentz group, not only the rotation part of the Lorentz. I mean, including the boost. Oh, the point is you see we have Z here, but also we introduce the delta here. Yeah, actually the delta is, roughly speaking, it's an eigenvalue of the boost. Okay. Yeah, so also we introduce the boost, and it's transferred to the delta here. Let me think about it. You mean a thing. So oh, you mean the R is the boost and the sphere is yes. Yeah. Because the Z and Z bar parameterize the sphere and the delta actually parameterize boost. I mean roughly speaking. Yeah. Yeah. Globally. I think it's not trivial factorization, but I mean, the point is we use the full parameters like delta z bar. It just gives us the same number of degree of freedoms as the on-shear momentum. Yeah, I mean, we can count this maybe roughly. For the on-shear momentum, we have three real degree of freedoms. Now we have z bar and delta, so somehow it's another 3 degree of freedoms. Yeah. So basically, this one just treats the omega I part to another delta, dual variables. Yeah. Okay. And this is the full dictionary. And so for the methods particle, the dictionary is just given by the mailing transform. As I say, I just perform the mailing transform on the energy part. And one important thing here is if we consider the collinear limit in the bulk, so the collinear limit, which is just to say we take two momenta be parallel to each other. And you will find the collinear similarity for the spectral amplitude is equivalent to the opposite product expansion similarity in CFT. So this is one thing important. Okay, so as I said before, the spectral amplitude can be derived by expanding the S matrix in terms of the conformal basis. So here I just give you some examples of the transform basis. The transform basis first satisfies some properties because first it should be conformally covariant. As I said, it manifests the Lorentz symmetry. So it must be conformally covariant. And another thing is because it's a basis of the space of the solution space, so it must satisfy the equations of motion. And the quantum numbers to label the transform basis includes the bulk mass, which is m, and the bulk spin L. Those two are both 4D parameters. And also have boundary parameters, which are conformal dimensions delta and the conformal spin J. So here is also different from the usual ADS-FT. In ADS-FT, we know the bulk mass is related to the conformal dimension, right? Because the equations of motions in bulk is just the Casimir equations in the boundary FT. That's why in ADS, the mass M is related to the conformal dimension. However, in celestial FT, this is not true. The mass M is somehow is an independent parameter. And the conformal dimension is independent of the bulk mass M. Okay? And another question is, how do we relate the bulk spin L to the conformal spin? Because now we have two types of spin. And for the massless particle, we know in 4D, the massless particle can be described by little group SO2, right? So basically, in the boundary spin, the bulk spin only have, for bulk spin L massless particle, it only have 2 degree of freedoms, which is plus helicity and minus helicity. And on the boundary side, we know a spin J primary operator in 2D safety also only have 2 degree of freedoms, right? If we go to the holomorphic and anti-holomorphic coordinates, we will get 2 degree of freedoms. So just at this level, you see the number of degree of freedoms match each other. So we can find that the bulk spin L massless particle will directly map to be a bulk spin L primary operator in the boundary. However, for massless particle, it's a bit complicated. Because for massless particle in 4D, the bulk spin L, the little group is SO3. And then we will have 2 L plus 1 degree of freedoms. However, on the boundary side, for boundary spin L, conformal spin L, we will also only have 2 degree of freedoms. To measure the degree of freedoms, which means a massive spin L particle will be mapped into the massive spin L bulk particle will be mapped into the conformal spin L minus 1, down to spin 0, conformal primary operator to match the numbers of degrees of freedoms. Okay. Oh, sorry. And for the massless part scalar, I give you one speed illustration for the conformal prime basis. It's just derived from the Planck basis by performing the Mailing transform. That's why the dictionary here is just a Mailing transform, because the bases are related to Mailing transform. Okay. Any question about this? Okay. And if there are no questions, I will go further this one. So here I introduce the conformal prime basis for massless particle, and also the dictionary for the celestial amplitude, which can be thought as conformal correlators. Then you say, yeah, since we have dictionary, we can compute or calculate some examples to show to see what's the AI, the celestial amplitude looks like. So actually, people indeed compute some examples, and they found some distorted properties of the celestial amplitude. Due to the momentum conservation, people found the 4-point celestial amplitude contains Dirac delta function with delta I times I T bar, theta chi minus 1. Here, the chi and T bar are conformal cross ratios appearing in the 4-point conformal correlators, and the theta is the step function. And those functions, these distributions, are actually do not appear in standard CFT. So this makes the celestial CFT more exotic. Due to the existence of this theta function, also the celestial amplitude does not admit the S-channel conformal Brownian expansion. So we know in safety, the four-point transform correlators can be expanded in terms of transform plot. And from the transform plot expansion, people can read off the spectrum of the safety. And to make the transform plot expansion convergent, people need to say the chi should be small. I mean, it should be in larger than 0, but smaller or less than 1 to make the whole thing convergent. But here you see we have theta times 1, which means the chi should be greater than 1. This one makes the central amplitude cannot be expanded into the S-channel transform plot, because otherwise the expansion is not convergent. Okay, so to resolve these issues, we can introduce the so-called shadow central amplitude by performing the shadow transform on the first particle. So here is the shadow central amplitude. Actually, the shadow transform is some periods, some integral transformations in safety, but which preserve the transform symmetry. Specifically, if we giving any transform primary operators in safety, you can derive another shadow operator by performing a shadow transform. This shadow operator also preserves the transform symmetry, which means it behaves like a transformal primary operator on the transformal transformation. But since this integral is not, since there is an integral, this is integral transformation, and that operator is not local operator. That's why usually people do not consider that shadow operator in safety, because it's non-local. Okay, now if we perform the shadow transformation, you say this one involve the coordinates integral. This will actually remove the delta function, right? Because the delta function will be removed by the integral, and also the theta function. And by using this, we can remove those distributions and just using safety techniques to study the shadow central amplitude. Okay, so I told so much about the central holography. Then you must, what's our goal of central holography? I mean, just like the ADSFT, this is when we want to study fault theory by using safety techniques, right? That's why people study using ADSFT. People want to use safety techniques to study the quantum gravity in ADS. So this is the same thing here. We want to study the stratum amplitude because that is most important observables in QFT by using safety techniques. Okay, so this is our goal. However, unfortunately, most of the work in central holography follows on opposite direction. People usually from the quantum gravity or quantum field theory in finite space and using the dictionary to calculate the celestial amplitude and try to figure out what properties the celestial amplitude should be satisfied. I mean, this doesn't make sense because people just know a little about the celestial safety. So people want to first get some hints or evidence. So people start from the QFT and do the translation to get the celestial amplitude and try to study the properties of celestial safety. So, but just remember our ultimate goal is using boundary sensitivity. I mean, go from boundary sensitivity to the quantum gravity in the bound. So this is the goal, which is another direction. Okay. So actually, our work, as I know, is the first work. I mean, construct the spectrum amplitude by using from the CCFT side, which is not just a translation, but we do the boundary reconstruction using safety techniques to recover the spectrum amplitude. Okay. So since we use some safety techniques, I will first review the safety techniques in safety. So the first one is the OPE, I mean the operator product expansion and the conformal block expansion in safety. So the operator product expansion is the most powerful tool in the conformal field theory, which says that a product of two primary operators in safety can be written as an infinite sum over a single primary operator and its descendant. So this is operator product expansion. Basically, you see, we reduce the number of operators from 2 to 1. right? And by using this, we can compute the higher point conformal correlation function from lower point one, right? Because for any endpoint, we can use the OPE to reduce it to be the n-1 point. And we can use the OPE again to be n-2 and then to finally to 1 or 2 point function, right? And for the OP here, the F is the OP coefficients, and the CA are called the OPE block or OP differential operator. And the one important thing is here, the CA is full filtered by the completely filtered by the conformal symmetry. It's telematic, and the dynamic information is encoded in the OP coefficients F550, and also the possible spectrum appearing in the sub, the O. These two encode the dynamic information about the safety, and the CA is purely telematic. Okay, and from let's say from the OP we can compute an interpolation function. For example, for 4-point function, we can use OPE twice. For example, we use OPE between 1 and 2, and also using OPE between 3 and 4 to reduce the 4-point function be a 2-point function. And the 2-point function in safety is completely filtered by conformal symmetry up to a constant, which tells a form like this. So from this, then we can rewrite the 4-point function as some known things with unknown OP coefficient and spectrum. And you see we just regroup this and did this. This is the so-called conformal block expansion, which means any 4-point function can be expanded into this conformal block, the little g here, small g here. And the small g is just the CA, CB acting on the 2-point function. Since CA, CB and the 2-point function are completely filtered by conformal symmetry, which means the g itself is completely filtered by conformal symmetry. And it's telematic, and we can compute it once, and this will work for any safety. Okay, so the only non-trivial information is included in the F550 and the spectrum O. This is the conformal block expansion. And you see, we do the OP for 1, 2, and 3, 4. This is so-called S-channel OP. That's the figure here, showing here. You may ask, could we do the OP, for example, between 1, 3, and 2, 4? Yes, we can do that. And we will get another conformal block expansion. This is a so-called T-channel conformal block expansion. And similarly, we can do the OP between 1, 4, and 2, 3. And we will get the so-called U-channel conformal block expansion. So you say, by performing the OPE in different ways, we will get the different expansion. And one important thing is, we just expand the same conformal correlators into different ways, right? So they must be equal to each other because they are the same conformal correlator. We just expanded into different ways. That's all. This is the so-called the crossing symmetry or crossing equations in safety, which is the foundation of modern conformal bootstrap program. Okay. So like I said before, the OP is associative, which means if we consider a product of 3 operators, we can first do the OP between 1, 2, and do the OP between the 3 and the exchange operator. Or we can first do the OP between 2, 3, and do 1 with another exchange operator. This should give us the same thing. This is the OP associativity. And if we put this associativity into the level of correlation function, we will find the correlation function will satisfy the crossing equation, which just say, as I said before, we expand the same conformal correlators into different channels. That's all. So this is a this is crossing equations in safety. Okay. Any question about this? Okay. So after I introducing the safety terms, then I can introduce what we have done in our work. So in our work, we basically found 2 things. The first, we derived a property of statistical safety. We found that the message strength amplitudes and thus statistical amplitudes can be derived from a single conformal block coefficient in statistical safety. So let me try to explain this. So here I show you an expansion in genetic safety. In genetic safety, this is actually an infinite sum. Or if you want to determine the full four-point function, you need to know the infinite number of the expansion coefficients F550, and also know the full spectrum. That's actually that is the case in genetic safety. That's also why the conformal bootstrap equation is very hard to solve, because it's an equation involving infinite numbers of coefficients. However, in safety, we found that for a four-point function, the F550 are not independent. You only need to know one of the F550, then you will determine all of the other, all of the rest coefficients. It's quite surprise to us, because you only need to know one, and you can determine infinite number of others and get the full correlators. This never happened in genetic safety. This is what we found special in safety. Okay. And due to that, due to these properties, then you see what we can do is how to determine the correlation function here in safety. We just need to figure out one of the coefficients, and using this one of the coefficients, we can determine the full selection amplitude. And from the full selection amplitude, we can then derive the full scattering amplitude. So this is our method. I mean, the basic principle of method. We're using safety techniques to determine the one coefficient, and from the one coefficient, we determine the full scattering amplitude and the correlators. Okay. Okay, so this is our development method based only on safety techniques. So to compute the scattering amplitude, as we say, we first determine a particular OP coefficient. This OP coefficient can be determined by symmetry, by the translation symmetry or asymptotic symmetries. I mean, people already know that. This is worked by Pate, Astronomer, and Yuan. And also, the second step, we're using CFT crossing symmetry. So basically, now it's the crossing symmetry for conformal correlators, now the crossing symmetry for standard amplitude. So we use CFT crossing symmetry. And using these two inputs, we can determine the full scattering amplitude. So as I know, this is the first example of using CFT to construct both observables. Okay, so now let me show you some example. Okay, I show you the first properties we derived. The conformal coefficient as flat space Mailing amplitude. You will see why we call it Mailing amplitude. Okay, so the property we found is massive scattering amplitudes and thus selection amplitude can be derived from a single conformal block expansion coefficient in CFT. So this is actually the exact relation we found. The C here is the conformal block expansion coefficient. So basically, if we better to here, this is just the F550 square appearing in this expansion coefficient. So basically, the C here is the expansion coefficient, and the S and the T here are manageable variables for 4-point scattering amplitude. We know we have, for 4-point scattering amplitude, we have two manageable variables, that is S and T. Oh, two independent one. You can also have U, but U is minus S minus T. So we only have two independent manageable variables. And the TST here is defined by this. The TJQI, this one is the full scattering amplitude, including the momentum conservation delta function. And the HJ here is a little group factor, which can be determined by the Lorentz group. Since we know for massive spin J particle, it has defined behavior on the Lorentz transformation. So basically, the H part is used to encode this behavior. And the H is also kinematic. I mean, it is the same in any theory. It's just determined by the Lorentz symmetry. And the dynamical information is encoded in the TST. So basically, we just separate the TJ into kinematic part and the Lorentz scalar part, which encodes the full dynamical information TST. And we found the TST is related to the conformal expansion coefficient by a twofold Mailing transform. And since for the conformal expansion, you see this one is the coefficient is labeled by the exchange operator O. So you may ask, what is the exchange operator related to the expansion coefficient here? So basically, we found the exchange operator related to this coefficient has conformal dimension delta 2 minus delta 1 plus 2 and spin J2 minus J1. The delta 2, delta 1 are conformal dimensions for external operators. And this is exactly the relation we found. So it's just a two-fold Mailing transform. If we can know what is the C, then we can determine what is the TST, and then we can determine the full T. So this is our law. So this is our method to construct the T. Similarly, CFT crossing-symmetry also implies that the same TST can be also expanded in T and U channel conformal plot. So basically, we found the T channel conformal plot coefficient also can be used to derive the TST and also U channel. Okay, and the alpha, beta are some linear combination of the conformal dimensions. Okay, any question about this formula? Yes, yeah. Yes. Oh, okay. You mean period from the conformal partial expansion or? Oh, okay. So the point is here. What I want to say here, the continuous just say the delta can be any continuous number. So we don't have any restriction to exclude any number for the delta. But if you have a specific theory, you can still find the conformal partial expansion and enclose the contour to pick up the radio to get some discrete number. Okay, so basically, what I want to say is, okay, the continuous just say for any sensitivity, there is no restriction to say it must be some discrete number. I mean, genetically it can be continuous number. But just like in genetic safety, the constraint we only have is from the unitarity, right? You just say the delta should be larger than some unitarity bound. But it's also possible it's continuous or discrete, right? How to say it's discrete or continuous? We just focus on some specific theory and do the computation. And if the spectrum is discrete, then we say it's discrete. If it's continuous, then it's continuous, right? Yeah. So in sensitivity, what I say continuous, just say we don't have. I just want to say we don't have any rules to guarantee that it should be discrete, but it can be. I don't know if I answer your question. Yeah. Okay. But, yeah. My point is, in sensitivity, you can still start from some conformal correlator and do the conformal partial expansion and pick up the residue. You will find in some case the residue is actually residue from single pole, so it gives us a discrete spectrum. However, if you find sometimes from branch chart, you may get some continuous spectrum. Okay. So let me before I talking about the reconstruction, let me give some comments on the C here. As I said before, the TST and the C are related by some Mailing transform. You see, it's very similar to the ADS Mailing amplitude. You start from some Witten diagram and performing the Mailing transform to get the Mailing amplitude. And here, if we see the TST as some Witten diagram, and the C part is just the Mailing amplitude in the ADS. That's why we call this as a Mailing amplitude in file space. And from this formula, we have found we know in TST side, the pole and the radial encodes the intermediate state and also possible unitary optional theorem utility in the theory, right? For example, if we consider the propagator 1 over s minus m square, we know the pole is at s equal to m square, which encodes the mass of the particle, right? So this is the analytic property of the TST encodes the exchange operators, I mean possible intermediate states and also the optional theorem utility in the TST. And on the other hand side, if we start with C, we found first C and T encode the same information because they are related by invertible transformation. So then they encode the same information. And we found the C actually manifests the UV and IR behavior of the TST. This can be seen as follows. Here we see this is a two-fold mailing transform. To compute this integral, usually we interpose the contour and pick up the pole by using the radial theorem to compute this integral. So now, if S, for example, S here is large, which means S here is large, which means we consider the UV region of the TST. When S is large, it's natural to introduce the contour into the right-hand plane, because now the contour is along the principal axis, which is parallel to the imaginary axis. So now we can, if S is large, we can introduce the contour to the right-hand plane, and using the radial theorem. So from this point of view, you see the pole and the radial of the beta at the right-hand plane encodes the UV behavior of the TST. And also, if S is small, which means the IR region of the TST, now then it's natural to encode the contour into the left-hand plane and pick up the radial and pole. So from this point of view, then we see the beta pole and the radial at the left-hand plane encodes the IR region of the IR behavior of the TST. Okay, and how about the alpha S property? So you see the alpha S is related to mass T over mass U. This one actually, mass T over mass U relates to the scattering angle. So the alpha S analyticity encodes the encodes the forward and the backward scattering limit of TST. Okay, so basically, that's what I want to say. The C and the T encodes the same information, but they manifest a different information of the scattering amplitude. This one manifests the UVIR and the forward and backward limit. Okay. And this one, since C is related to TST by a two-fold mailing transform, C can be thought as 5-space mailing amplitude. And one future derivation I want to mention is, we know now there are so many work on mailing bootstrap to bootstrap the mailing amplitude in ADS. Now we have similar object quantity, the C, which is also related by TST by mailing amplitude. So by mailing transform, then it's natural to us to develop a similar tool like mailing bootstrap to bootstrap the C and then into the flat space amplitude. Yeah, this is what we want to explore further. Okay. So after you talk about this, let me show you how to reconstruct the scattering amplitude by using this relation. So to get T, we first need to determine C. Okay, and remember here the dimension is delta 2 minus delta 1 plus 2, and J is J2 minus J1. Okay. So now the first example we consider the MHV of 4 gravitons. So it's a bit long trivial example because it's not stellar, it's a graviton. We know the interaction can be complicated. And we consider the 1, 2 scattering into 3 and 4. And here the helicity are labeled as the particles are outgoing. Okay, so basically if you see, if you just consider 1, 2 is incoming, so the plus plus here should be mean minus minus if we treat those two particles as incoming particles. Okay, so this is the MHV amplitude of graviton. And to compute this, we need to determine the C. So basically we need to use the OPE. And the OPE of H is partially determined by symmetries. I mean, because we know that there can be infinite number of exchange operators appearing in the OPE, but using symmetry, we can determine one specific OP coefficient appearing for the H. Okay, H here is a gravity operator. So I have two H, it changes another H. And the OP coefficient is a beta function given by this. This beta function can be determined by transition symmetry and a subtotal symmetry. So the point of view, we don't need to know the Lagrangian or the addition or anything. We just use the symmetry to fit the coefficient. Okay. However, this gravity operator has spin +2, right? But using this formula, the exchange operator should be J2 minus J1. Now the J2 and J1 are both 2, so JS should be 0, which means we should force on the exchange operator of a scalar. But now this operator is a spin 2. So how to do it? Get that scalar, because now we just know the OP coefficient of spin 2. Okay, so this reach our key point of the reconstruction. One natural possibility is that the exchange operator is a primary descendant in the transform family of gravity. So first, we assume that because we consider the pure gravity theory, we should somehow how to say that believe that, maybe not just believe that, the exchange operator should be built out from this H. Okay, and now we want to transfer scalar. And in the transform family, there is a scalar, which is partial bar square acting on the H++. This is actually a scalar. However, this is a descendant, right? So now we have another issue. Now we have a scalar, but it's a descendant. But in CFT, there is a special thing. When the transformer dimension is equal to some special value, this descendant will could transform as a primary operator. This is a so-called primary descendant in CFT. And this you can just determine this by transform algebra. You will find if the delta is equal to 1, the partial bar square H is both descendant and primary. Okay? So now we assume that is this primary descendant appearing in our operator expansion and appearing in the transformer expansion. So the primary descendant implies that the delta 3 plus delta 4 should be equal to 1, which means the whole dimension of the partial bar square acting on H should be equal to 3. On the other hand side, we know the transformer dimension of the exchange operator is delta 2 minus 1 plus 2. Delta 2 minus delta 1 plus 2. So to match the transformer dimension on both sides, we did this equality. This is just a dimension matching. Okay? And furthermore, we assume that only this primary descendant contributes to the transformer block expansion. So this is so-called minimality condition. We don't know what's the physical meaning of this one. We conjecture that this may relate to the minimal toppling of the MHV amplitude, of the pure gravity and the pure QCD theory. Okay, by using okay. Yeah, it's the same one. But actually, in principle, you can find some other operators with the same dimension may contribute to the transform block expansion. But here we assume there is only this one. Okay, yeah. Okay, by using these conditions, from the OPE, we see the transform block expansion coefficient can be written as a product of the OP coefficient and the 3-point coefficient, right? Because if we use OP once, here, we will get the OP coefficient times the 3-point function, right? Because the OP only reduces the number by 1. So in this sense, the transform block expansion coefficient can be also determined by OPE coefficient and the 3-point coefficient. And the 3-point coefficient, we can compute it. It's not hard. But by computing this 3-point coefficient, we actually, for this special case, we do not even to compute it. Because in this one, we know the graviton at the tree level have some definite staining behavior. We can just use the staining behavior to argue that the three-point coefficient must be proportional to this, to a delta function. And the C here is just some constant we don't hit. And it's proportional to some delta function. And the conformal expansion coefficient is the product of OPE coefficient and the delta function and the three-point coefficient. So now we reconstruct the CS by using symmetry and staining behavior without Lorentz addition or Lagrangian or interaction vertices, right? Now with the CS in hand, we can just substitute the CS into our formula here and try to compute the TST. Okay, so by using this, we did the TST, take the formula like this. Here we introduce another thing, NS. This is the ambiguity. Because, as I said before, to compute the alpha S and the beta integral, we need to encode the contour and the pita of the radius, right? And in this case, you see the pole nigh on all of the integers. I mean, from the negative integer, all of the negative integer and the positive integer, and also zero. So then we will ask which poles we should pick up, or which poles will contribute to the contour integral. Because without any knowledge, we don't know where is the contour located at, right? So this is the ambiguity. And the NS is the first pole living at the right-hand side of the contour. So basically, when we choose the contour, we count the contribution from NS plus 1, NS plus 2, to infinity. So there is an ambiguity from the contour location. And to fix this contour ambiguity, we can use another safety theory, is the crossing-symmetric. So basically, here we compute this one in S channel. We can also compute the whole thing in T channel OPE. Just repeat the step, just the same thing. And we found the TST from the T channel OPE gives us this. Okay? Now, cross-symmetry tells us the two results must be equal to each other. This will fix the NS and the NT, and give us the final answer is this. Okay, and we check this. This is exactly the 4-point MH way to graph the amplitude in the literature. They first compute this by Feynman rules. But you see now we don't say anything about Feynman rules, anything about addition, anything about Lagrangian. We just use safety, assuming the cross-symmetry of OPE. We derive the MH amplitude of 4 graviton. We bypassing the complicated Lagrangian, right? Okay, so you may say this is just so happen in this result we have the right result. So we check more. The first, here I use a figures to show the cross-symmetry. So we can this is S channel with this exchange operator. We can also expand the TST into T channel with this exchange operator, and they give us the same answers. Fix the TST given by this. Okay. And now we consider another more complicated one. We consider the graviton coupled to the gluon. So it's the so-called Einstein-Yang-Mills theory. Now we have more complicated Lagrangians and interaction vertices. We just repeat our steps by using safety things. And now the process is driven by this. In S channel, the exchange operator is another primary descendant, and this is also a primary descendant. And by just repeating the previous steps, we get the final answer is driven by this. Here we consider 2 gluon get staggered to 1 graviton plus another gluon, and we get the static amplitude is this. The FABD here is the color structure, into the color structure. Again, we check this answer. It's matched with the Lorentz result in the Einstein-Yang-Mills theory. But again, you see we don't say anything about Lagrangian and the Feynman rules. We just get these answers by using safety. Finally, we also compute the QCD, MH of 4 gluon in QCD. And we consider the 1, 2, 7, 2, 3, and 4. And at the tree level, now there is a additional thing which is made the whole thing complicated is we have the Taylor structure. And in 4D, we know we have the Taylor structure only have two independent bases. Two independent Taylor structures form the basis, which is ABE, CDE, or ACE, BDE, or we can use ADE, BCE, and ACE, BDE. We only have two, because another one is related to this by Jacobi identity from the group theory. Yeah, the Jacobi identity of structure constant just give us this constraint of the T1, T2, T3, T4. And also, we know the whole thing should have permutation symmetry on the permutation of 3 and 4. Give us this identity. Okay? And then by following according to the structure constant, you see, for example, for the T1, the structure constant is ABE and CDE, which means this one can be constructed from the S channel because we do the AB OPE and the CD OPE. And the same thing for T2, T3, T4. And we just following our method. We do the reconstruction. We do the T2, T3, T4 is given by this. Finally, we're just using these identities. We finally fix all of things, give us the full de Luan amplitude, including the Taylor structures, Taylor constants. Again, we just use safety. We do not use anything about the Lagrangian or Lagrangian from QCD or any Feynman rules. Yeah, this is how we give the scattering amplitude by using safety. Okay. Okay. So finally, let me give you some future dimensions. First is the relation we found between the T and the C is purely non-perturbative. Okay, this is a non-perturbative relation. So which means if we can find a way to fix to take the C non-perturbatively, we will get the T non-perturbatively. Here in our work, we only get the tree level results. That is because the input for the C is the tree level result. That's why we use the tree level TST. But anyway, I want to stress that our relation is purely non-perturbative. If we input non-perturbative C, we will get the full result of TST. So basically, this gives us a way to compute the non-perturbative scattering amplitude. And another thing is, what is the bottom origin of the session OP and the minimality condition? That's I don't know. We don't know. We just guess that maybe it's related to the minimal toppling in the theory. And the third thing is, here we only talk about the massive scattering amplitude. It's natural to ask if we could extend the result to massive. And actually, we already have some progress in this way. We found that if we consider one massive and three massive scattering amplitude, we can find similar relations. And using this, we already construct another non-trivial amplitude, which is one Higgs boson detached into 3 de Luans. We, using our way, repeat the result. That one is quite non-trivial. Because if you want to compute that one in Feynman rules, you will turn some loop contribution, Fermi loop, and then get the tree level one Higgs boson decay into 3 de Luans. However, in our case, we didn't say any loop because we just input the OP coefficient. We did the same result, and we'll try to do more about it in this way. Okay, another thing is higher point. You see, if you know, for MHV, people already have BCFW reduction relation to let people to allow people to compute n-point MHV amplitude, right? So it's natural to us to extend our result to higher point one, and we found we can. We also have some progress on this. Here I show you one result we already have from the 4-point scattering amplitude to 5-point scattering amplitude. So the whole integral gave us the 5.1. And the T tailed is amplitude relates to 4-point scattering amplitude. So you see from this way, we check this for scalar case, it works. And you see in this way, we already have some return relation from lower point to higher point. We're already working on this to get a full thing. And but something you can say is this is totally different than BCFW retention relation. So from this way, we expect that we can get some retention relation from CSFT, which is totally different than BCFW. And they basically they can be applied to different situations and to get amplitude. And what's important is, as I said before, our retention relation can be used to compute the loop amplitude. However, as I know, in many cases, BCFW does not work at the loop level. But our retention relation can be used to compute loop amplitude. We're also trying to do this. Yeah, that's all. Thank you.
The audience. Oh, okay.
So just like how you get the celestial amplitudes from the conformal blocks in the celestial CFT, do you know if there's a similar method to get a Carolian amplitudes from Carolian CFTs?
Yeah, actually, I don't know that much about Carolian. Yeah, I know people already have some dictionary between Carolian and the central CFT. However, what I want to mention is, I know that there is one issue. I think it's a very important thing need to be solved is in central CFT, people know how to the dictionary for the massive particles in the bond, right? Because we know in the QFT we also have massive particles, but in central CFT, people know how to deal with that massive particle. However, in Carolian CFT, as I know, people do not find the dictionary for the how to map the massive particle into the Carolian field. Yeah, I think that's actually I'm working on that with my collaborators. I think that should be important because we know we have massive particle. We should solve this issue. Yeah.
Any other questions? Maybe I can ask one.
Okay.
So we know from like just the computation of celestial amplitudes, we have like this higher spin currents and also the soft theorems. Yeah. I was wondering if you can recover those things from just by looking at like the celestial CFT OPEs and your computation. Is there a hint of like the soft theorems showing up, basically?
Okay. Yes. Actually, it is. Okay. So actually, for the soft theorem, there is in CSFT there is equivalent stuff. So they call it conformally soft theorem, which means if you take the conformal dimension into some spatial value, you will rid off the soft contribution from scatter amplitude. For example, for the delta here, this is for reference. If you take the delta equal to some minus integer or some negative integer, or I mean some integer less or equal to 1, you will rid off the soft contribution. And here you see when the delta 4, for example, is equal to some negative integer, we have pole from the beta function. And actually this match with the prediction because to get the conformally soft limit is actually pick up the residue of this one. And we try to this by taking the residue on the OP side, we will get the soft algebra. And the people found that soft algebra will generate the W1 plus infinity algebra. Yeah, this is how people get the whole thing from the OP.
Okay.
Yeah.
And you also see that the soft part just factors out, right? Like from the structure of this B. Okay. Seems that like the majority of the mystery is hidden in this B.
Yeah, hidden in this beta function actually. Yeah.
Okay, nice. If there are no more questions, then let's thank the speaker again.
Thank you.